Okay, good afternoon, guys. My name is Gavin Rivera. I'm the integration lead for ARES 6. Our student-led design team is working to manufacture the first liquid-fueled rocket to launch to 45,000 feet with a pressure-fed bipropellant system. Thorough research and analysis and performance sit behind our designs, as most of our rocket system is designed in-house. Diving into our analysis further, we have most of our rocket system um, Diving into our analysis further, we have confidence in the following changes made to our rocket system. We will now be featuring an ablative-cooled engine outsourced to the company CompositeX. With this change, we will redesign our injector to a liquid-liquid doublet injector. We have introduced a static fire test stand senior design team to model after University of California, San Diego SEDS chapter's test stand. This will allow us to test and analyze our rocket engine's performance before it launches. Today, you will hear from our propulsion team led by Ben Bartnick, our powerhead team led by Victor Sponer, our aerostructure team led by Abby Feeder, and our test stand team led by Tyler Nance.
Sorry about that. I was muted. I'm Ben Bartnick. I'm the propulsion team lead. I'll be taking over in the spring semester, and I'll be giving the preliminary design review today. I'll have Tanner Tripoli presenting with me, and he'll be presenting on the igniter system. We break our propulsion team down into 3 sub-teams of the combustion chamber, the injector, and the ignition system, just to keep things a bit cleaner and a little bit more organized as we go through our work. Our goals overall for the future and for this year are cold flow test by the end of this year, a static fire test by October of next year, a launch and successful recovery in May 2022. And these are hard dates for our goals. We would like to achieve them by then, if not before then. And that launch should be 45K. But the timeline for this year is a bit aggressive. Hopefully, it's not actually that aggressive. Hopefully, we get a design in for our injector by November and get that to us by early January so we can assemble our rocket, or not our rocket, our tests in February and get a water flow and a cold flow test done by the end of the year. As was stated before by Gavin, we are switching from a regen cooled system to an ablative chamber and nozzle, just to reduce complexity and mainly the cost, bringing the costs down from $25,000 to around $6,000. We're going to be outsourcing that to CompositeX just for safety, so that any mistakes in the manufacturing process won't be caused by students who may be inexperienced when it comes to the designing and manufacturing of parts. This also helps to accelerate our timetable to launch, as we do not have to learn how to make all of the parts for the combustion chamber and nozzle ourselves, and increases our chance of success when it comes time to that. CompositeX has a motor shown in the bottom left corner that they've done before. They use a metal and they wrap it with a composite and put the orange ablative inside it, and they've had great success with this. We have an old design in the CAD model here, but all the dimensions will remain the same because we're getting the same performance out of it with the same combustion chamber pressure of 406.22 psi, the same burn time of 16 seconds, the same thrust of 1151, and the same OF ratio of 2.7. That doesn't change when we switch from a regen cooled design. The injector design, as stated before, is switching to a doublet injector to allow for better mixing of 2 liquid fuel states, since we switched from a coaxial, which mixes a liquid and a gas better. This will allow for hopefully less hot streaks in our flow through our combustion chamber and our nozzle so that it can burn for 16 to 17 seconds so we get the maximum performance and achieve our desired altitude. Obviously, we need to test this, which is why we plan on doing a static fire before we take this out to a launch so we know just how well our ablative performs and just how well our injector performs in protecting that ablative. It's going to be using a methane and liquid oxygen system with a flow rate of around 1.985 kilograms per second. And now I'll hand it over to Tanner Tripoli to talk about the ignition system.
All right, so yeah, as Ben said, my name's Tanner. I've been working on the ignition system this semester. Right now we have an Aerotech motor which produces 444 kilowatts of power and a minimum ignition power of 150 kilowatts for our liquid oxygen methane mixture. This is left over from this is like pretty much entirely last year's design. And we'll also be using the design from last year of the internal integration mount, which positions the motor inside the thrust chamber, and it will clamp down onto the nozzle. And when the motor is fired, it will stay ignited until combustion occurs in the combustion chamber, at which point it will be ejected. Our power supply for this system is going to be external to save on weight. And it's the most important part about this project is getting the ignition timings down, so that way it doesn't delay for too long and then there's too much fuel and oxidizer in the combustion chamber and would give us a hard start that might damage or destroy the combustion chamber as a whole. It's also equally bad if, it's not equally bad, but it still is bad if the motor does not ignite, because then we will have to wait several hours before we can even approach the rocket for fear of someone getting hurt. And we'll also have to purge the system. And since we don't have any system built into the rocket to purge it because of weight constraints, we'll have to wait for a while. So in order to avoid this from happening, we'll be doing extensive testing on the rocket throughout this semester and next semester. Some things that need to be tested are the ignition timings for the Aerotech composite starters we're using with the Aerotech motor, and we'll need to consider the effects of the cryogenic environment inside the combustion chamber. We'll need to consider the effects it will have on the ignition sequence. All of the hardware that's required for this testing has already been ordered, and we're waiting for its arrival within the next few weeks, and we hope to get our first test done before the end of the semester. And we'll be doing all of these tests at the Tuscaloosa Airport in line with NAR safety standards, meaning we'll have to have at least 100 feet of distance away from this H-class solid rocket motor. And we'll need launch keys in our launch control system, which we bought off the shelf to avoid an accidental ignition. All right, I'm gonna give it back to Ben now. He's gonna talk about the tanks.
The tanks that we inherited will be explained further by the Powerhead team, but we're currently working with Worthington Industries to manufacture a cryogenic COPV fuel tank, an oxidizer tank, and pressurant tanks, which will carry our liquid methane, liquid oxygen, and our helium. And it is kind of unusual and uncommon to use a COPV fuel tank and COPV pressurant tank, but Worthington Industries has worked with us to ensure the safety in this manner and to make sure that it's safe for launch and ready to go on time. The budget is a lot cheaper than last year because we switched from a regen cooled design to an ablative, bringing down the cost to around $6,000 because we'd like to have 2 combustion chambers and nozzles, 2 static fire and 1 to launch, so that we know what we are getting into before we go for a launch. With that static fire, the injector is priced around $1,850, the ignition system around $200, bringing us to around $1,150. We'll get harder numbers as the parts and components come in and we add, but these are looking like our masses currently, bringing us to around a total of 112 pounds for the entire system. Any questions